Okay, so let's start. Um, any questions from the previous class? No questions. Okay, so last class was of course just introductory, wherein we defined the kind of optimization problems we are interested in studying. So a general optimization problem, the kind that we are interested in, can be posed as the following. So we are given an objective function f defined over some variable x, and the goal is, let's say, to minimize this function f of x subject to some set of constraints g of x greater than or equal to b. Right? This is one way of posing a general optimization problem. Another way of looking at this is saying that we want to minimize f of x subject to x lying in some subset s. Right? Basically, S is the set of all x that satisfy all the constraints. Right? So S is what we call the constraint set. So in this general framework, where the goal is to answer a set of questions. So first, does a solution exist? Does an optimization problem necessarily have a solution? Does it have to have a solution? Okay, what can happen? When does this problem not have a solution? Yeah?
Constraints are not tied.
Constraints are not?
Tied.
Uh, can you be more precise? Okay, but can you kind of elaborate on when? Forget about minus infinity or plus infinity. What else can happen? What did you mean by constraints not being tight?
Constraints don't constrain the solution to certain.
Okay, but that may still be okay.
Domains of the two functions might not be tested.
Can you refine your answer a little bit? You're thinking along the right direction.
The constraints contradict in a way. So let's say constraints, the constraint set basically is some s, whereas the objective function can be optimized only in some set s component or any set where.
So the function is well defined over, let's say, Rn, right?
S is pi does not.
S is
Pi.
it's empty, right? It's possible that the constraint set is empty because these constraints are not simultaneously satisfied, right? So in general, no, because this particular set may be empty. Right? If it is not empty, then we say that this optimization, there exists a feasible solution. So So any value of the variable that actually satisfies all of these constraints is called a feasible solution. Right, so for example, if I say that x has to be greater than or equal to 0 and less than or equal to -1, then this is obviously this set of constraints does not have a solution. Yep.
With your x, you would use it less than.
Sorry, was I using less than or equal to? Sorry, right. G of x less than or equal to b. Okay. So now firstly we have to determine if the problem has a solution at all. In the second case, now if there is a solution, is the solution unique? Not necessary. Can you give me an example of an optimization problem where you have multiple solutions? Can you give a more specific example? Y equal to x square. So f of x equal to x square. But what are the constraints? Okay. So suppose I take f of x equal to x square minus 1. Where will it be minimum? It will be at x equal to 1. The minimum. Sorry, x equal to 0. So there exists a unique solution for minimizing this particular problem. Any other example? Yeah? Mod, you mean mod of x square minus 1. Okay, what is the solution for this? Plus 1 minus 1. Right. So there exist two different solutions. You can take anything minus x square. Right. The minimum is of course minus infinity and plus infinity. So in general, solutions may not be unique. Right. Particularly when you have constraints, it may get even more complicated. So these are two questions, but the third more important question is, how do we find the solution? Just because a solution exists doesn't mean that we can very easily find this particular solution. So to address each of these steps, we'll start with optimization over just the reals. We'll look at functions over the reals. In particular, in this course, we'll be interested in convex functions. So let me define that first. We'll see how convex functions behave over the reals, and then see why our intuition can potentially fail when we go to higher dimensions. Right, so Alright, so can one of you recall what the definition of a convex function is? So let's say that f is a function from R to R. So the argument is a real value and the function value is also real. When is f said to be convex? Yes, anyone? Okay, so one definition is second derivative is greater than or equal to 0. But does it hold for all functions? The second derivative must exist at all points, right? Should be twice differentiable. Is there any other definition you've seen before? Yeah? That's way ahead. We don't know what is positive semi-definite yet. But we're looking at functions on R, right? Have you seen it?
The range must belong to a convex.
Okay, that's the range of what should belong to a convex set? Okay, but why is that sufficient for it to be convex? Okay, intuitively, when you think of a convex function, what do you think of? What does it look like? Yep, so it should look like a bowl or something like a quadratic, right? X square. So the intuitive picture is that the function looks something like this. Can we sort of formalize this intuition a little bit? Yep. But you can take for any function as long as it is well defined, there will be a minimum, right? And moreover, I can think of functions like this. Is this convex? No, right? So, okay, so I'll give a mathematical definition. We'll see what it means in just a moment. So I'll say that f is convex if for all x1, x2, so I take any 2 points and I take an arbitrary number between 0 and 1, f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha f of x1 plus 1 minus alpha f of x2. Okay, let's try to see what this definition actually means. Let me take this example here. Okay, so let me pick any 2 points. Let's say this is my x1, this is my x2. Okay, and correspondingly I have this here is f of x1, this is f of x2 along the y-axis. So what is alpha x1 plus 1 minus alpha x2? Where does it lie? Right, so it will lie somewhere in between x1 and x2. Do you all agree? All right, so I take x1, I take x2, these are two real numbers. The set of all alpha x1 plus 1 minus alpha x2 for alpha between 0 and 1 essentially corresponds to the straight line joining x1 and x2. Correct? In particular, if I take alpha equal to 1, then I just get x1. If I take alpha equal to 0, then I just get x2. So if I take any alpha strictly between 0 and 1, I'm going to get a point in between x1 and x2. So let me pick some point. Suppose this is my alpha x1 plus 1 minus alpha x2. Okay. So what is f of alpha x1 plus 1 minus alpha x2? That's essentially the function value at this particular point, which is this. All right. But now what is alpha f of x1 plus 1 minus alpha f of x2? What does this correspond to? Right. So that just corresponds to the straight line joining f of x1 and f of x2. Correct. So particular this. Right. So alpha f of x1 plus 1 minus alpha f of x2 would lie somewhere here. For example, if I took alpha exactly equal to a half, then this would be somewhere midpoint of this. Similarly, this would correspond to the midpoint of this particular line. So what does this definition tell us of convex functions? It says that if I look at the straight line joining f of x1 and f of x2, then this is always going to lie above the curve corresponding to f of x. Right? So this right hand side is the straight line joining f of x1 and f of x2. Right? So as I vary alpha between 0 and 1, I'll get all the values along this particular straight line. On the other hand, the left hand side corresponds to the function value between f1 and between x1 and x2. Right, so as you vary alpha, f of alpha x1 plus 1 minus alpha x2 essentially just varies along this particular curve. Right, so another way of defining a convex function, so it's a function where the value of the function is always below the straight line joining any 2 points on that curve. Okay, is that fine? And this works for any function. It could be differentiable, it need not even be continuous for that matter. Okay, so now we've defined a convex function, right? But there's also probably you've seen another so-called definition of a convex function, which says that a function is convex if the second derivative is always greater than or equal to 0 for all points. Right? So we'll treat this as the definition of a convex function. Okay, and try to show that those two notions are equivalent if the function is twice differentiable. So suppose we have a function f which is twice differentiable, then the following two statements are equivalent. So f is convex and the second derivative of f is greater than or equal to 0 for all x. Right? So similarly, just as we've defined convexity, we can always also define concavity. Right? Now, given this particular definition, how would you define a concave function? So greater than. So essentially, a function is concave if the straight line joining 2 points on the function always lies below the function value. Right? Since we already have the definition of convexity, I can say that a function f is concave if minus f is convex. Right? Is that an okay definition? Okay. So these two, for twice differentiable functions, these two definitions are equivalent. Alright. So I'll prove this particular result, but even before that, let's see some examples of functions. And we'll try to prove that these functions are convex or not convex. So let's take So can you give me some examples of convex functions to begin with? X square. Let's take f of x equals x square. So again, let's assume that this theorem is true. So we can use it if we want. How do we prove that this function is convex? So
taking it line for things taking -1 and 1 or something.
okay.
0 is lying in between, and the value is always less than the line joins.
But that's only one point, right? You have to prove it for all points on the line.
But we are getting a minimum at the
So
double Asian to the point. So getting the minimum for it for the whole function and zero.
I take a function like this. Is this convex? This is convex?
Yeah.
Is it convex?
For all points it will be.
I'm talking about functions over R, right?
So,
It's not convex.
yeah.
So that's not sufficient. You have to verify that this property is satisfied for all x1, for all x2, and for all alpha between 0 and 1. Right? But what is an easy way to prove that x square is convex? Just take the second derivative. What is the second derivative equal to? Equal to 2 for all x, right? So it's convex. Okay, let's take e to the power x. Yeah, convex. And why? Take the second derivative. What is the second derivative of e power x? Prime of x equal to e to the power x, which is greater than or equal to 0 for all x in R. Yeah.
This convex function is trying to satisfy that complex structure.
Which?
Convex functions.
Sorry, what structure?
Means if you draw the graph of that function,
Correct.
is it necessary to be a complex structure?
Again, what do you mean by cup-like structure? So,
Pouch.
sort of, yes.
How economics?
Well, again, when I say bowl-like structure, it doesn't necessarily have to have a minimum, right? Sorry, a real valued minimum. So this is a function which is monotonically increasing, right? But it's still convex. Not satisfied? So this is going to be a definition for a convex function, right? That's why I've said that may or may not have, if I'm optimizing over R, it may or may not have a minimum, point of minimum, right? So what would be the minimum of e power x?
0.
Minimum value is 0, but it's achieved at minus infinity, right? Which is still going to be okay. Okay. In particular, if I impose some constraints on this, let's say I'm trying to minimize e power x over some particular interval, where will the minimum value be achieved? Right, so the left end of that particular interval. Okay, so it's not necessary that when I have a constrained optimization problem or even otherwise, the minimum will be achieved in the interior of that particular set. It could be at one of the ends. And we'll see that this will become an issue as we go later on. Okay. But no matter what happens, even if I take e to the power x, if I take any 2 points on the curve and I draw the straight line, it is always going to lie above the curve. Right? That's something you agreed. Right? So it is going. So this is convex. What about e to the power minus x? Is it convex? Right? What is the second derivative? This is also greater than or equal to 0 for all x. Okay, let's take log x. Log x, but of course this is defined only for x strictly greater than 0. Yeah. Concave. And why is that? Okay, so let me take the second derivative. This is minus 1 by x square, which is less than or equal to 0 for all x in R, for all x in 0 to infinity, so concave. But both these are convex. Right, let's maybe take something a little more complicated. 1 by 1 plus x square. See. Why? Okay, what is the second derivative equal to?
Yes.
Okay, what is the first derivative equal to? 2x 1 plus x square whole square. That's it. There is no negative sign.
Minus.
Okay, what is the second derivative equal to?
x square.
What is it?
4x square by 1 plus x square.
4x square by,
Oh, so that's correct.
it can't be that simple. Minus 2x to the power 4 plus 8x cube. 4. Can you slow down? Minus plus 8x minus 2. Sorry, 2 upon 1 plus x square whole cube. Is this correct?
K square minus.
So is this function convex? Why? Can you give a point where the second derivative is?
X3 minus 1 by
So this is so let's try to plot this function and see what it looks like. Minus 20, 20. So this is what it looks like. So it's obviously not convex or concave. Okay, so let's take another example. F of x equal to mod x. Okay, it is it's convex. Do you all agree that it is convex? So it's just going to look like this. Right, but how do we prove that this function is convex? Okay, how? Firstly, can we use the second derivative test here? We can't, because it's not differentiable at x equal to 0, right? What happens if I try to use it? Or why does it fail? Yeah? It's not defined for x equal to 0, I agree.
Tan will have different, it has two different directions.
Okay.
So is towards the right and x squared towards left. We get also.
That's the first derivative. But what would be the second derivative at all other points? It's 0 everywhere, right? So can you give me an example of a function which let's say has the same second derivative, but you know for sure is not convex? Or an example where the second derivative test fails. 1 minus mod x. You can just take minus mod x, right? If I take minus mod x, what is the second derivative at all points except 0? It's 0, right? But is this function convex? It's not, right? It's clearly concave. So the second derivative test is not enough if it is not differentiable even at one single point. Okay. So to give another example, let's take the following weird looking function. Say f of x equal to x square for x less than or equal to 0. And it is, let's say, x square plus 1 for x greater than 0. Is this function convex? So let's look at this particular example here. Convex. How many say it is convex? Show of hands. This function that I've written, f of x equal to x square when x is less than or equal to 0, and x square plus 1 when x is greater than 0. It's not continuous, sure. That's why I have this example. How many say yes, it is convex? How many say no, it is not convex? Okay, why is it not convex?
Straight line.
Yeah,
Right.
right. So if I, it's x square. So what does the function look like? It's looks like this, but then at this particular point, it's like this, right? So intuitively, if I take, let's say, a point over here and a point over here, and I draw the straight line joining these 2 points, it is convex. That's exactly why I have this example. It is it differentiable at x equal to 0? How? Is it continuous at x equal to 0? Right, so it's not differentiable. Yes, it's not continuous, so it can't be differentiable. So it's not differentiable only at one point, right? Just one single point, and that's enough to change convexity properties. If I take a point slightly to the left of 0 and a point slightly to the right of 0, and I draw the straight line joining these two, there is one point where the curve lies above the straight line and one point where the curve lies strictly below the straight line, right? In fact, even if I take just x equal to 0 and x just above 0, these are going to lie on opposite sides of this straight line. So this function is not convex. No. So function could be convex, it could be concave, it could be neither convex nor concave. Right? So, for example, let's take f of x equal to x cube. Is this convex or concave or neither? This is smooth, it's continuously differentiable, right? So what would be the second derivative? Yeah, 6x. For x greater than 0, this is always non-negative, always positive. For x less than 0, this is negative, right? So if you take this function over all of R, then this is neither convex nor concave. But then if you restrict yourself to only one region, let's say x greater than 0, then this is convex. For x less than 0, this is concave, right? So let's...
But previous function was not concave as well.
Not convex, not concave. So once again, if I restrict myself to a sub-interval, right, the set of all positive real numbers, then this is convex. If my domain is the set of all negative real numbers, then again this is convex. But if I take all of R, then this is neither convex nor concave. So this is what f of x equal to x cube looks like. So I look at just the positive reals. Maybe I should. If I take only the positive reals, then this function is convex. If I take only the negative reals, this function is concave. But if you take all of the reals, then it's neither convex nor concave. Okay, so let's go back to our example, f of x equal to mod x. We know that this function is convex, but how do we prove that this function is convex? Okay, let's try to. So the left hand side is f of alpha x1 plus 1 minus alpha x2. Right, and what we want to show is that for every x1, x2 and alpha between 0 and 1, this is less than or equal to alpha f of x1 plus 1 minus alpha f of x2. Okay, what is this equal to? It is mod of alpha x1 plus 1 minus alpha x2. What can I use? Yep, I can use triangle inequality to say that this is less than or equal to alpha x1 plus mod 1 minus alpha x2. But this is also the same as alpha times mod x1 because alpha is always greater than or equal to 0 plus 1 minus alpha mod x2. Right, which is exactly alpha f of x1 plus 1 minus alpha f of x2. So this is a function which is not differentiable at one point, but it's still convex. So let's go back to the result, the equivalence result between convexity and that the second derivative is always greater than or equal to 0. Okay, so remember we have two things to show. We have to first show that if f is convex, then the second derivative is always greater than or equal to 0. Second thing is, if the second derivative is greater than or equal to 0, then f is convex. It's an if and only if condition. So let's pick one side. Let's say that suppose that f is convex. Okay, which means that for every x1, x2 and alpha, f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha f of x1 plus 1 minus alpha. So we have to use this to show that the second derivative is always non-negative. Okay, so how do we prove this? What expressions do you know for the second derivative of? How do you compute the second derivative? Okay, using limits. So in terms of limits, do you know what is second derivative evaluated at x? Okay, what is the first derivative equal to? So limit as, let's say, t tends to 0 of f of x plus t minus f of x divided by, right? Similarly, what about the second derivative of x? Yeah, f dash of x, but can I get it directly in terms of f of x? Yeah, you can substitute, sure. So you may have to be a little clever with it. So let me just give it directly. Let's take limit t to tend to 0 f of x plus t plus f of x minus t minus 2 times f of x whole divided by t square. So basically I look at f of x plus t minus f of x divided by t minus f of x minus f of x minus t divided by t whole divided by t. Okay, is that okay? Yeah, so t tending to 0 from the positive side. T tending to 0 from the right. Yes. Because if not, there can be a sign change in this particular definition. Yeah. Or whatever, t tending to 0 plus, if that's what you're more used to. Okay, so let's try to use this to show that the second derivative is always greater than or equal to 0 for a convex function. Now let's look at f of x plus t plus f of x minus t. We want to somehow be able to represent it in as some combination, convex combination of f, right? So let us consider, let's start with maybe f of x. Okay, I can write this as f of x plus t by 2 plus x minus t by 2, right? Which is just f of half of x plus t plus half of x minus t, right? Which is in the form alpha x1 plus 1 minus alpha x2. So what can I say about this for a convex function? This is less than or equal to half f of x plus t plus half f of x minus t, right? So what can I say about f of x plus t plus f of x minus t minus 2 times f of x? Right, so if I just take the 2 to the left hand side and bring that to the right hand side, then I just get f of x plus t plus f of x minus t minus 2 f of x is greater than or equal to 0 for all x. Is this okay? Well, since this is greater than or equal to 0, this quantity should always be greater than or equal to 0 because t is greater than or equal to 0. So this limit is always going to be greater than or equal to 0. So the second derivative is also going to be greater than or equal to 0. Okay, so we proved one half of the result. So if f is convex, then the second derivative is always greater than or equal to 0. Now let's prove the second half. So let's suppose that the second derivative of some function is always greater than or equal to 0 for all x in R. Okay. Now we want to say something about the convex combination, right? I want to say something about alpha f of x1 plus 1 minus alpha f of x2 minus, let's say, f of alpha x1 plus 1 minus alpha x2. Alright. So just to make things convenient for me, I'll define x equal to alpha x1 plus 1 minus alpha x2. Okay. So what I want to show is that alpha f of x1 plus 1 minus alpha f of x2 minus f of x, I want to show that this quantity is always greater than or equal to 0. Alright. So I'll rewrite this in a certain fashion. This is equal to alpha times f of x1 minus f of x plus 1 minus alpha times f of x2 minus f of x. Okay. So I make another assumption. Let's just take x1 to be less than x2. Okay, without I can do that without loss of generality. Say x1 is less than x2. So if I take the function I have x1 here, I have x2 here, and x lies somewhere in between. Okay. So now that I have this, let me see what I can do. So do you recall the mean value theorem from your calculus? F dash of. So geometrically, what does the mean value theorem say? So suppose I have, so let's quickly recall the mean value theorem. So I have some function and some particular function, and I take 2 points x1 and x2, and I draw the straight line joining x1 and x2. Alright, what does the mean value theorem say? There exists at least one point in between, as long as x1 and x2 is the function is smooth. The slope equals so there exists at least one point where the slope of or the derivative, correct. So the tangent to this particular curve is parallel to this particular line. So there's some point where the tangent is parallel to this particular line joining f of x1 and f of x2. If I had to put that mathematically, then the mean value theorem says if f dash of x exists for all x in x1, x2, then there exists some, let me call it x prime in x1, x2, such that the derivative of x at x prime equals the slope, which is f of x1 minus f of x2 by x1 minus x2. So if I apply the mean value theorem to each of these two terms, what would I get? So I'm taking the following sets of points x1, x. Okay, so this is x1, this is x. Let's say that the function is indeed convex. I'm taking this point, I'm taking this point, and I'm looking at this. Maybe I should take x1, x and x2, right? So I have f of x1 minus f of x. I'm saying that there exists some point where the tangent is parallel to this particular line joining these 2 points. So mathematically, what would this give me? This would be equal to, so there exists some, let's say, beta 1 which lies in between x1 and x, such that what will be equal to x1 minus x times the derivative of f at beta, right? Let's call it beta 1. And there exists some beta 2 that lies between x and x2, such that this is equal to 1 minus alpha x2 minus x times f prime of beta 2. Okay, now let's just substitute for x. What do I get? Alpha times, what is x1 minus x equal to? That depends on this order, right? So if this is f of x1 minus f of x, then this should be x1 minus x. This is x minus x1, then this should be x minus x. That's why you have to be careful. So here it is f of x2 minus f of x. So this is x2 minus x. So what does this evaluate to? x1 minus x. So what is this first term equal to? So alpha into 1 minus alpha into x1 minus x2, right? Or I'll write it in a different way, minus of x2 minus x1 plus 1 minus alpha into, sorry, there's an f prime of beta 1 it is alpha into x2 minus x1 times the derivative of beta 2. So this is just alpha times 1 minus alpha times x2 minus x1 times the derivative of beta 2 minus the derivative of beta 1. Right, it's okay so far. Now, these three terms are all non-negative, right? Because x2, we've chosen x2 to be greater than x1. Alpha and 1 minus alpha, of course, non-negative. What can I say about f prime of beta 2 minus f prime of beta 1? Why? So first, where do beta 1 and beta 2 lie? Right, so where does beta 1 lie? So beta 1 lies between x1 and x. Where does beta 2 lie? So it lies between x and x2. So clearly beta 2 is going to be greater than beta 1. That is something we know. But does it mean that the derivative of f at beta 2 is greater than the derivative of f at beta 1? Can you think? Yes, so the double derivative is always greater than or equal to 0. So what can you say about the derivative? It's an increasing function, right? So if the derivative of x greater than or equal to 0 for all x, this implies that f prime of x is increasing. Or to be more precise, non-decreasing.
Second last time.
I'm sorry, where? Here. There is an alpha here. So 1 minus alpha into x2. So the second derivative is always greater than or equal to 0. This implies that f prime of beta 2 is going to be greater than or equal to f prime of beta 1, which means that the whole quantity that I'm interested in, which is alpha f of x1 plus 1 minus alpha f of x2, the left hand side, minus f of x, this is always greater than or equal to 0. So the function is convex. Right. So if the function is twice differentiable, then these two notions of convexity are the same, which becomes very convenient, because many functions that we're interested in, we can just test convexity by just finding the second derivative and finding whether it's greater than or equal to 0 or not. All right. So this was a convex function. Now if I want to minimize a convex function, what do I do? Suppose that the second derivative exists, and you know that it's always greater than or equal to 0. So what is the technique that you've learned in high school for minimizing a convex function? Take the derivative, set it to be equal to 0, right? Essentially just solve for the first derivative of x being equal to 0, right? But why is this the minimum? Yeah,
Because it's convex, the slope is parallel to the x-axis.
correct. So
So
the slope becomes 0 at the point. Yes, that's what this f prime of x equal to 0 says.
if we draw any line above, like if we take any 2 points other than the point,
Okay,
the equation, like function will always be less than the.
that is true. That's true for any point, right? Any 2 points. How do you argue that this should be the point of minimum? Yeah.
Take any 2 points on either side and
Okay.
then compare it with the values that
Okay.
so at that point, the derivative in either direction will be positive.
Correct.
Check it that.
Correct.
Then that must be, if we check for all such points, then that becomes the optimum for the convex.
Right. So, in other words, so let's say that x star satisfies the first derivative of x star equals 0, right? So since the second derivative is always greater than or equal to 0, the first derivative is always an increasing function. That's what we've seen, right? So for all x less than x star, the first derivative is less than or equal to 0, right? So for all x less than x star, what kind of a function is f? It's a decreasing function, right? Which means that f is for x less than x star, correct? What about x greater than x star? This is always greater than or equal to 0, which implies that f is increasing. Which means that f of x will be greater than or equal to f of x star. So on either side, the function value is greater than f of x star. So it should be the point of minimum. So all of this is fine. So one-dimensional optimization is at least intuitively clear. So if I'm giving you an arbitrary f, if you can find if it is possible to compute the derivative of f of x, then minimization of f of x essentially corresponds to solving this particular functional equation, right? Trying to find an x such that the derivative equal to 0. Yeah. But x is less than x star, right? If f of x is decreasing and x is less than x star, then f of x would be greater than or equal to f of x star. Right? So geometrically, you take x star, to the left of x star, f of x is a decreasing function. So it should look something like this. To the right of x star, f of x is an increasing function. So it would look something like this, which must mean that this is indeed the point of minimum. Okay. Now it may seem that fine, this was all obvious and I'm unnecessarily trying to complicate things by deriving things rigorously. But this will be important when we're dealing with higher dimensional objects. Everything is straightforward, the geometric intuition is clear in one dimension. But we're interested in much more complicated optimization problems. So we need to understand how things behave in higher dimensions, but by getting intuition from lower dimensional functions. Right? Our imagination just stops after dimensions 2 and 3. Okay. So just to illustrate how things can quickly get very complicated, let's look at the following example that arises very frequently in wireless communication. Okay, let's look at the so-called capacity of a multiple antenna channel. So of course I will obviously not derive the capacity of this, but as it turns out, suppose I am given a channel. Let me just explain the physical problem and give you the solution or the capacity of that particular problem. So consider the following scenario where I have multiple antennas. So I want to communicate through wireless medium. I have multiple antennas at the transmitter and I have multiple antennas at the receiver. Right? And I'm allowed to communicate through this noisy medium. Okay. I of course need a model for this noisy communication channel. So let's suppose I have NT transmit antennas and NR receive antennas. Then a reasonably good model for this communication system is at any time instant, I'm allowed to send one real value on each of these antennas. Of course, I'm assuming some kind of modulation inherently, but one way of modeling this particular problem is that I transmit a vector of length nt in one time unit, and I receive a vector of length nr. Essentially, this is the value of, you can think of it as the modulated symbols that are transmitted on each of these antennas. Right? So I can transmit NT modulated symbols on each of these NT antennas, and correspondingly I get NR different values, the measurements at each of these NR antennas. These are the demodulated symbols. So a reasonably good model is at any time instant t, yt equals some matrix h times xt plus some noise vector zt, where this h is an nr cross nt matrix, xt is essentially an NR length vector, sorry, NT length vector, and YT and ZT are NR length vectors. Okay, this is one particular model, and ZT is typically taken to be Gaussian with mean 0 and variance sigma square. So there are NR components. Each component is independent and distributed according to a Gaussian. Okay, let's not worry about where this came from, but this turns out to be a reasonably good model for approximating this particular communication system. Now, for this particular scenario, I'm interested in knowing what is the maximum number of information bits I can send in one time instant. On average, what is the maximum number of information bits that I can send while also satisfying a reasonably low probability of error. Okay. So if you recall the example in the previous class, we were interested in finding out what is the maximum rate for a given probability of error constraint. And as it turns out, the maximum rate of reliable communication so this maximum rate, this is sometimes called the capacity of the channel. This turns out to be the maximum. Of course, now what am I allowed to do? I'm allowed to send any symbols, but at the same time I also have to satisfy some power constraint, right? And we'll see how that power constraint. So at any point xt square on average should be less than or equal to p. All right. Right. So this is a maximum of log of the determinant of a certain matrix. This matrix is I sigma square I plus H A H transpose, where A is going to be a covariance matrix. So this maximization is overall A, which is positive semi-definite, and the trace of A is less than or equal to P. Okay, let's not worry about where this came from. Okay, but these are the kind of optimization problems we're interested in solving, right? Because this exactly tells me what is the maximum rate I can transmit through a particular channel. How should I allocate different rates for different users? If I have multiple users, all of whom are trying to communicate through some kind of a through such channels, I want to know, I have to decide, right? So that involves solving an optimization problem that looks something like this. So firstly, we don't even know what this function looks like, right? It's a function of over matrices, and not just arbitrary matrices. The maximization is taken over only positive semi-definite matrices. So we need to be able to understand what these constraints look like in the first place, for which it's very difficult to get any sort of geometric intuition. And secondly, we have this function which is log of determinant of some particular thing. Is this function convex? We don't know at the outset. As it turns out, this function is indeed convex when the corresponding argument is over the set of positive semi-definite matrices. And these are the kind of objects we're interested in handling, right? So So we'll try to develop theory to analyze such functions of this particular kind, wherein we may not have intuition. We'll still try to take intuition from our simple examples like 1 dimensions and 2 dimensions and over Rn, but we still want something general that works even for such complicated scenarios. Right? So in the next couple of classes, we'll go over the basics. We'll try to see the basics of multivariable calculus that can handle objects of this kind. Right? So let's stop here. Any questions?